I'm going to prove a beautiful statement about binomial coefficients, which is an introduction to number theory proofs. And at the end of this video, I'm going to give you a peek into advanced mathematics based on this statement, which states that if p is a prime number, then the binomial coefficients p choose I are all divisible by p as long as 1 less than or equal to I less than or equal to p minus 1. So obviously, if you take p choose 0 or p choose p, you're going to get 1, which is not divisible by p. P is a prime number, but every other binomial coefficient is. And we're going to get into this proof, and it's really a nice, elegant argument, and what's so beautiful is its applications, which I will show you at the end. So let's first start off with the proof. So what's going to happen with the proof is we're going to have to use the fact that p is a prime number, because this isn't true in general. Okay, it isn't true in general. So for example, if you take 4 choose 2, then 4 choose 2 is equal to 4 times 3 by 2 times 1, which is going to equal to 6, which is not divisible by 4. But 4 is also not a prime number, so that's okay. But if p is a prime number, p choose I is divisible by p. So why is that? Well, p choose I is going to equal to the following. If you think about how you explain how you get a formula for the binomial coefficients, it's going to be p factorial by I factorial times p minus I factorial. Okay, that's going to be what it is. And it's an integer. Okay, so it's an integer. And that's actually quite interesting. We know that, and we want to now show that this is an integer divisible by p as long as I is between 1 and p minus 1. Now here's the interesting thing. Let's look at the numerator of this integer. Okay, the numerator of this integer is divisible by p, right? It's divisible by p. There's no problem there because it's p factorial, which is p times p minus 1 times p minus 2, etc. The denominator, on the other hand, is not divisible by p. Why is that? Well, the denominator is not divisible by p because p is a prime number. And this is why we're going to use the fact p is a prime number. So let's think about what the denominator is. The denominator is I factorial times p minus I factorial is just going to equal to I times I minus 1 times I minus 2 all the way up to 1. And then you're going to multiply with times p minus I times p minus I minus 1. And again, that's going to go times dot 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 times 3 times 2 times 1. Okay, all the way up to 1. Now, here's a fundamental property of prime numbers, and I'm going to show you the proof of that in the next video, but it's actually very intuitive. Okay, so it's very intuitive, but it needs a rigorous proof, is that if p divides a product of numbers, and if p is prime, then p has to divide one of the numbers. So in this case, if p did divide the denominator, p would have to divide one of these numbers in the denominator. But given that I is between 1 and p minus 1, right? I is between 1 and p minus 1, that means that p cannot appear in any of these. P can't divide any of these numbers because they're all less than p. And p can't divide any of these numbers because they're all less than p. And so since p is prime, p cannot divide the product. So we've used the fact p is prime to say p cannot divide the product even if it doesn't divide any of the individual numbers, which is not true for non-prime numbers. Like 4 divides 2 times 2, but it doesn't divide either of the factors 2, basically 2 and itself, 2 and 2. Okay, so because of that, p divides the numerator but not the denominator. So therefore we conclude that, okay, p divides p factorial, that's a divide symbol. P does not divide I factorial times p minus I factorial. Therefore, p divides p choose I so long as 1 less than or equal to I less than or equal to p minus 1, and that is the proof. Now, why is this statement so interesting? So I'm going to show you something called freshman's dream. Okay, and it's freshman's dream because it's a common misconception in freshman level math in university or even in high school, I guess. And it's the following statement, which I'm going to show it to you right here. The statement of freshman's dream is the following. So I'll give you one example of it. There are many variations of it. The first example is a plus b squared is a squared plus b squared. Now, if someone states this, it's an error, but actually it's not an error in certain number systems, specifically if you work in the number system modulo 2. So in other words, you look at the remainders when you divide both these quantities by 2. What are the remainders? And they're actually equal. So this side is even if and only if this side is even, this side is odd if and only if this side is odd. Okay, and how that works is basically because the real answer for a plus b squared, we know the actual answer is a squared plus 2ab plus b squared. And if you reduce modulo 2, in other words, 2 becomes 0 because you're dividing you're looking at remainders when you divide by 2. So if you add on 2 times AB, that's an even number, so it's effectively not going to change the parity, whether the number is even or odd. So if you take the remainder of this when you divide by 2, it's the same as the remainder of this when you divide by 2, which is a squared plus b squared, and we write that modulo 2. Okay, so that's the symbol here, that's just these two are equal modulo 2, which means that their difference is divisible by 2. They have the same remainder when you divide by 2. And this actually comes from the fact that the coefficient here is actually 2 choose 1, which is kind of a simple case of what we just proved. But if I took something like the following, suppose I took a plus b power p, where p is a prime number. Okay, so I'm going to write that as follows, p is a prime number, and I expanded this out. The binomial theorem tells me, or tells us, that this is going to be a power p plus p choose 1 times a power p minus 1b plus dot 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 plus p choose I times a power p minus I times b power I, and then it's going to keep going, plus dot 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 plus b power p. Okay, so we're going to get this expression here. And if you look at this expression here, then what you notice is that each coefficient, p choose 1, all the way up to p choose I, okay, this is p choose I, I'm just going to write that neatly, all of these are going to be divisible by p. So when you take remainders when you divide by p, all of those are going to equal to 0 modulo p. In other words, they're all divisible by p. So the remainder of this whole expression when you divide by p is the same as the remainder of just a power p plus b power p when you divide by p. So this equation is true modulo p. Okay, so these two quantities have the same remainder when you divide by p. So this is what is called freshman's dream in general, and it's a consequence of that theorem there. And actually, I can even explain this in one more advanced level of math. I'm going to state it on this side of the board. So you're going to love this. This is high level math, so I won't explain it in a lot of detail, but I'll give you an idea. There are interesting number systems where p equals 0, where p is a prime. So what that means is that in the number system, you have the concept of 1, which is just a multiplicative identity. 1 times anything is just going to be that thing. And when we say p is equal to 1 plus dot 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 plus 1 p times. Okay, and it turns out that this is equal to 0. A common example of such a number system is modulo p. When I just talked about this, for example, we can say 0, 1, 2, all the way up to p minus 1, with the understanding that addition and multiplication are taken modulo p. So when you add two numbers, if they go beyond p minus 1, in reality, you divide by p to get a remainder in this. Okay, so this stays within the system, addition and multiplication, and this is called, this is called z mod pz typically. What you can do is, in this case, 1 plus 1 plus 1 p times is equal to 0, and in such number systems, this is an example of one, but there are many, many others. In such number systems, there is this function called the Frobenius p, that I'll just denote such a number system by x. Okay, it goes from x to x, and what it does is it just takes a number x in the system and takes its pth power, x power p. And what's very interesting is this map is what is called a homomorphism. It respects all the laws of arithmetic. So for example, x plus y power p is always going to equal to x power p plus y power p, and actually we proved that in this video, because as I said, we know that the binomial coefficients p choose I are all divisible by p, so we established it here. It doesn't matter, and we don't need to know anything about the number system. That's really cool. It's a very abstract statement. We know that because p choose I is divisible by p for all 1 less than or equal to I less than or equal to p minus 1, we know a plus b power p is a power b plus b power p, and another thing we know is that x y power p is equal to x power p times y power p. Okay, this is not something that's as difficult. It's just x, y, etc. So as long as you can swap x and y around, which is called the commutative law for multiplication in our system, we can just say that x, y, etc. p times is x times x p times, and y times y p times. In other words, x power p times y power p. This is what is called a homomorphism. It's very interesting that in this system, this map, Frobenius p, this function, is actually the identity function. Okay, it doesn't actually, anything power p is actually congruent to itself modulo p. Okay, and so that's not so interesting in that for that reason, but that's a statement, that's basically Fermat's little theorem. But in general, if you have a number system which is characteristic p, you have this Frobenius map, and it's fixed points. The points where it is sending an x to itself, x power p is equal to x, are precisely somehow this number system 0, 1, 2, 3 up to p minus 1, which exists in the bigger number system, and these are all the points that are mapped to themselves by Frobenius. Okay, so I've gone into a lot of more advanced concepts which I haven't explained in a lot of detail, but You can be sure there'll be videos on that in the future. My math has all levels across all topics in math. If you want to know more about what I just said here, please drop a comment down below. Check out my next video. You're going to love it. It's a rigorous proof that P divides AB implies P divides A or P divides B. It's popped up on the screen here. And another fun video you're going to love is going to pop up on the screen here. It's a solution of the Pythagorean equation, finding all integers A, B, and C that could be the side lengths of a right triangle. 3, 4, 5, because 3 squared plus 4 squared is 5 squared, but there are many, many others. You can actually solve for all of them, and that's going to pop up here. Hope you have an amazing day. Loving the content on my channel.